In this video, we're going to return to linear differential equations, and we're going to talk about the problem of getting that particular solution. So in a non-homogeneous case, remember that your solution will be one particular solution plus the general solution to your homogeneous differential equation. We've talked about getting that, and then we know that we add that to any particular solution, and then that will be your overall general solution. But the catch was finding that one particular solution. Where does that come from? Where do you get that? Okay, so that's the issue here. And I'm going to give you a first strategy as far as that goes. There's a strategy that you can use when it's a constant coefficient case. So remember, that's dy dt equals a constant times y, and then plus b of t. Okay, so to explain how this works, I'm going to work an example. So let's say dy dt equals negative 3y plus, and for my b of t, I'll put e to the 2t. All right, so remember, what we're looking for is any solution to this differential equation. And then, like I said, we'll add it to the homogeneous, which we can figure out with no sweat, and then we'll be good. All right, well, here's the idea. If I move the minus 3y over to the other side just for a second, right, I get that the derivative of y plus 3 times y is going to be e to the 2t. Okay, well, whatever the formula is for y, right, whatever we put here, whatever ends up going here for our particular solution, when you take the derivative and then add 3 of itself, you're supposed to get e to the 2t. Now, in a way, what the strategy here is just a guess, but it's going to be a very, very educated guess. What could possibly be in this formula? Well, what I'm going to say is that it kind of has to be something involving e to the 2t. Now, it might not be exactly e to the 2t, but I'll give us a little bit of leeway. I'll put a coefficient in front. I'll call that alpha. Alpha e to the 2t. Now here's the thought process. Obviously 3 times that will just be a multiple of e to the 2t. And I know how derivatives work with exponentials. I know the derivative will also be a multiple of e to the 2t. So this will be a multiple of e to the 2t, this will be a multiple of e to the 2t. And when I add them together, I want to get one single e to the 2t. So that makes sense. It makes sense that there wouldn't be other terms here, sines, cosines, powers of t, because I know that when I take those derivatives, those are just other powers, or the derivative of sine is cosine, the derivative of cosine is sine. So I'm just getting junk that I know isn't supposed to be over here. So unless it perfectly canceled out on the left, that's doing me no good. So the simplest thing is to let's just assume that since I want to get e to the 2t out of this combination of y and its own derivative, let's assume y is just a multiple of e to the 2t. And now the only thing then is to figure out what multiple of e to the 2t it is. So what we do is we plug this in. So like, this is our guess. We're going to plug it in and see if we can make it work by making alpha be the right number. So let's see. So the derivative of alpha e to the 2t is 2 alpha e to the 2t. 3 times alpha e to the 2t, okay, 3 alpha e to the 2t. And on the right-hand side, I still have my e to the 2t. So it looks like I'm getting 5 alpha e to the 2t equals e to the 2t. And I can very easily make that work if I pick my alpha to be 1/5. If I pick alpha to be 1/5, that'll cancel with this 5, and I'll have a true statement. And that will mean that this will have worked. So my particular solution is 1/5 e to the 2t. So again, it was just kind of a guess as to the form, but an educated guess based on my b of t that was given to me. And then it was just plugging it in and seeing what my coefficient had to be. So this is called a well, it's a guess, and it's called the method of undetermined coefficients. So we sort of we centered in on a particular type of formula of a certain form, but with only the coefficient not determined, and then we just plugged it in and saw what the coefficient had to be. And this will work for a lot of cases. Again, we are assuming we have a constant coefficient here. If there's t's involved here, then this could get a lot harder to try to do it this way. And if we have a pretty reasonable right-hand side, in other words, a pretty reasonable b of t, we can come up with a pretty good guess. Now let me just finish off this problem so you can see the thing in its full in its full details. So remember, that's our y of p. That is not, very likely not going to solve the initial condition that we have. If you plug in 0, you can see that yp of 0 would be 1/5. So, if our initial condition was 1/5, then we've got our answer, but chances are it's not. So this guy isn't the final answer. So what we have to do is go back to our linearity principle and add the homogeneous general solution. So for the homogeneous general solution, that is the homogeneous differential equation is dy to t equals minus 3y. I just get rid of the b of t part. And this one is the type of differential equation that we immediately know the answer to. We know that it is c e to the minus 3t. And so our final general solution is y equals 1/5 e to the 2t plus c e to the minus 3t. And that's it. As usual, any initial condition you actually want to solve for, you plug it in here and you can figure out what c is. Here's another one. Suppose dy to t equals 4y minus 3 cosine 5t. Okay, linear, constant coefficient, 4, and here's my b of t. So I want a particular solution. I'm going to move the 4y over. Dy dt minus 4y equals negative 3 cosine of 5t. Now, what makes sense for a guess? Well, yeah, I need whatever y is, it and its derivative have to combine in this way and give me a cosine of 5t. It seems like I'm probably going to need a cosine of 5t in my solution. But in this case, I have to think a little bit more carefully. Now, if y is cosine of 5t, I know that my derivative is going to therefore have a sine in it. Now, if I just went with cosine, I'll have cosine here, I have cosine here, but then this guy will have a sine that's not over here. So what I'm going to do is I'm going to include a sine of 5t as well. And I'm going to put undetermined coefficients in front of them. So some amount of cosine 5t plus some amount of sine 5t. And what I'm going to hope for is that when I put it all in here, and I put it and then its derivatives, and I work it all out, that I can get the sine stuff to cancel away to 0, and then the cosine stuff to give me exactly what's on the other side. That's the hope. Let's see if it works. Okay, so this is my guess. All right, I plug it in. So, of course, the derivative, so that's going to be minus 5 alpha sine 5t is the derivative of my cosine. And then I'll have plus 5 beta cosine 5t. All right. Now I have minus 4y, so minus 4 of this. So minus 4 alpha cosine 5t minus 4 beta sine of 5t. And I want this to equal on the other side simply minus 3 cosine of 5t. All right. So what I need now is I need the sine stuff to cancel itself. So I have minus 5 alpha sine 5t and minus 4 beta sine 5t. So I need minus 5 alpha minus 4 beta to end up being 0. I need that because I don't have any sine over here, so the sines here have to cancel. And then I need the other two guys not to cancel, but to give me what I do have over here. So I need 5 beta minus 4 alpha to be negative 3. If I get both of these things to happen, that will mean I have a solution. So I need to find an alpha and beta that satisfy both of these. Okay, now this is just a sort of a straightforward algebra problem. It's just a linear system, 2 variables and 2 unknowns. We talk about this a lot in other classes. You can solve it sort of in a old high school way of substituting one into the other. You can do you can do elimination, or you can also use more of a linear algebra matrix approach. Let me just fast forward through that. In our face-to-face class, we can talk about the details there if you want, but just to keep this brief, I'll just fast forward through the algebra part. Okay, the solution I get is alpha equals 12 over 41, beta equals negative 15 over 41. And check that works, or actually, like I said, make sure you are able to get those numbers from the two equations doing some sort of algebra. Okay, so therefore our particular solution we now have. It's going to be 12 over 41 cosine 5t minus 15 over 41 sine 5t. That's our particular solution. Now, remember the whole point now is to combine that with the homogeneous general solution, and we're good. So the homogeneous differential equation is simply dy dt equals 4y. We drop the b of t just for a second. So that's easy. That's y equals e to the 4t with a constant in front. And so our final answer is 12 over 41 cosine 5t minus 15 over 41 sine 5t plus arbitrary constant times e to the 4t, and that's it. We get our general solution. Any initial condition could be used to figure out the capital C. Okay, so this is a method to get the particular solution in a linear differential equation that has constant coefficients. Again, this method doesn't really work too well if it's not constant coefficient. Also, let me just finish by saying, if your b of t is an exponential, that's what you guess. You guess the same exponential with a coefficient in front. If your b of t is a sine or a cosine, you guess the same sine or cosine and the other one. So we had cosine 5t, so we guessed a cosine 5t and a sine 5t with undetermined coefficients in front of those. Those are the two big ones. Other cases, if this gets more complicated, it might be harder to make a guess, but those two are the biggest. Maybe the other one would be powers of t. We can talk about that in class, or you can check it out in the book.